Hi guys, today we're going to take a look at question 5 of the 2017 exam paper 2. Okay, so the first part of this question is just outlining things that we can already see on the diagram. So we can see that ABCD is a rectangle, F is on the line AB, G is on the line BC. The intersection of FD and AG is E, and FD and AG are perpendicular, which we can see because this is a right angle. So all of these are information that we can already see, and then they've given us these lengths that we can see because they've put that onto the diagram as well. So we want to look at part A, prove that the triangle AFE and DAE are similar or equiangular. So as they've kind of alluded to there, similar means the triangles have equal angles. Have equal angles. Okay, so we want to show that this triangle here, this triangle in the top corner, has the same angles as this triangle ADE. Alright, so we want to show that these two have equal angles. And so, well, what do we know? We know that, because they've given it to us, that this is a right angle. And since this is a right angle, and this is a straight line, this also has to be a right angle. So we've shown that angle FEA equals angle AED. So that's one angle we've shown to be equal. Okay. Well, now let's just call this angle number 1, number 2, number 3, and number 4, just so we don't have to constantly be saying angle F, A, E, F, D, whatever. Okay, so because AFE is a triangle and our angle here is a right angle, this angle here, then angles 1 plus angle 2 is equal to 90 because there's 180 degrees in any triangle, and the other angle is 90. Okay, and so we also have, since this is a right angle, angles 3 and angles 4 are equal to 90. That's just for the same reason, since there's 180 degrees in any triangle and the other angle is 90. Okay, and so now we also have, since the whole thing is a rectangle, this angle here is a right angle. So angles 2 plus angles 3 is also 90. Okay, and so we know that, so if we put this equation with this equation, angle 1 plus angle 2 equals 90, and angle 2 plus angle 3 equals 90, so angle 1 has to be equal to angle 3, because when you add angle 2 to either of them, you get the same answer. And then if we look at here, this equation plus this equation, angle 3 plus angle 4 is 90, and angle 2 plus angle 3 is 90, so angle 2 is equal to angle 4. for the same reason, because when you add angle 3 to either of them, you get 90. So we've shown that this angle is equal to this angle. We've shown that this angle here on the little triangle is equal to this angle on the big triangle, and we've shown that they both have right angles here. So AFE have equal angles AFE and DAE. So these two triangles have equal angles, equal angle 1, equal angle 2, equal angle 3. So they are similar. Now on to part B, find the length of AD. So let's clear up this diagram. So we're looking for this length AD. And so, well, what information do we have? Well, we know that the triangles AFE and DAE are similar. So that means they have equal angles. But it also means that their sides are in proportion. That's the interesting characteristic of similar triangles. So their sides are in proportion. So AD over AF, the sides opposite the right angles, is equal to FE over AE, the shortest sides of each triangle. So let's write that down. So the length of AD over the length of AF, sides opposite the right angle, is equal to AE over FE, the sides opposite the shortest angle. Okay, so we know that AE is 12 and FE is 5. So AD over AF is 12 over 5. But the problem is we don't know what AF is. And so we can't find out what AD is. So what is AF? Well, what we do have here is we know that AFE is a right angle triangle. So we should immediately be thinking of Pythagoras' theorem, a squared plus b squared equals c squared, where a and b are where c is the hypotenuse and a and b are the other two sides. So in this case, the other two sides, FE and AE, are 5 and 12. So 5 squared plus 12 squared should equal the square of the length of the hypotenuse, and the length of the hypotenuse is the length AF. So 5 squared plus 12 squared is AF squared, which is 169 equals AF squared. So if we take the square root of both sides, square root of 169 is AF. So AF equals 13. AF equals 13. And so now we have enough information here to solve this. So we have the length of AD over the length of AF, which is 13. And this is a fairly easy equation to solve. We just multiply both sides by 13 and we get AD equals 13 by 12 over 5 equals 31.2 centimeters. We're working with centimeters. And so that is our answer for the length of AD. So just using the knowledge that if triangles are similar, then their sides are in proportion, and then combining that with Pythagoras' theorem to find the length AF. Now on to part C. The triangle AFE and the triangle AGB are similar. Show that the length of AB is 36 centimeters. Again, so let's clear up our diagram. So the triangle AFA, our triangle in the top corner, is similar to this triangle ABG. Which makes sense because ABCD is a rectangle, so this should be a right angle. And both of them have this angle here. And so the other angles just have to be equal, because the sum of the three angles equals 180, and the other two angles are the same. So if two triangles have two of the angles equal, they also have to have the third one equal. So it makes sense that they'd be similar. Okay, and so what did we just talk about with similar triangles? Their sides are in proportion. So in this case, we're looking for AB. So AB is the angle opposite the bigger side that's not the hypotenuse. So AB over AE should be equal to, so let's just write that down, AB over AE, the sides opposite the bigger angle that's not a right angle, should be equal to the hypotenuse AG, the side opposite the right angle, over the other hypotenuse. So AG over AF. So the hypotenuse over the hypotenuse. Okay, and so we know what AF is, we just found it. AF equals 13. We know what AE is, it's 12. And that just means we have to find AG, and then we can find what we're looking for, AB. But finding AG is just very easy, because E is on the line AG, and this portion is 12 centimeters, and this portion is 27 centimeters, so the whole thing is just 12 plus 27 centimeters equals 39 centimeters. Okay, and now we have three of the lengths and we're looking for the fourth, so this should be fairly easy. So we've got AB over AE, which is 12, equals AG 39 over AF 13, and that equals 3. So if we multiply both sides of these two equations by 12, we get AB equals 3 by 12, 36 centimeters, which is exactly what we were trying to prove. Now on to the fourth part, part D. Find the area of the quadrilateral GCDE. So we're looking for the area. Let's just clear this up again. We're looking for the area of this shape, GCDE. Now this is a bit of an awkward shape to try and find the area of. We don't really have a nice formula for a weird area. But what we could do is find the area of the whole shape, ABCD, and then minus the area of these triangles here. This triangle plus this triangle. And then that would make it fairly easy. So let's write out an equation there. So we know that the area of the whole rectangle is the area of the rectangle. That's just the rectangle ABCDE. Sorry, ABCD. ABCD is equal to the area of this weird quadrilateral. Let's just draw something like this. GCDE plus the area of the triangle ABG this green area here plus the area of this triangle AED, the blue, plus the area of AED. Okay, and we can calculate all of these areas. We know how to calculate the area of a rectangle and the area of triangles, and that will allow us to get what we're looking for. So if we rearrange this formula, then we get the area of this quadrilateral, the area of GCDE is equal to the area of, let's just call this ABCD minus the area of ABG minus the area of AED. Okay, and now this gives us a manageable way of answering the question. So let's focus first on the rectangle ABCD. Well, the area is just length by width. Where the length is AB and the width is AD. And we already have these two lengths. This is just AB equals 36 by AD, which is 31.2. So the area of ABCD is 1123.2. Okay, and now if we focus then on ABG, well, we know we have the formula for a triangle, half the base times the height, the perpendicular height. But that's easy to calculate with a right angle triangle because the perpendicular height, so in this case, is just this length. So we're looking for half of AB times BG. So half the base, the base is BG, half BG by AB. And we have AB, but we don't have BG. So what is BG? Well, this should be pretty simple to calculate because we know that this triangle is similar to AFE. And so this length, BG over 5, so BG over 5, the sides opposite the shortest angle, will be equal to these, because the sides are in proportion. So BG over 5 equals 3. That's what the ratio is, which we found here. And so BG is just 15. So the angle of this triangle is half by 15. So half by 15 by 36, the length of AB, which is 270. So that's the length, that's the area of ABG. And now onto the area of AED, the final thing we have to calculate. So that's the area of this triangle AED. So that's half the base, again, our formula for a triangle, half the base by the height. So that is half the base, which is AE, which we have, by the height, which is ED. Which we don't have. So that means we need to find ED, but that's just the same way that we found BG. We know that it's similar to AFE. So ED over AE, ED over AE, the sides opposite the bigger non-right angle, is equal to 12 over 5, the sides over the shorter angles, equals AE over FE. So ED over 12 AE is equal to AE 12 over FE 5. So multiply across by 12 and ED is equal to 144 over 5. So then that allows us to get AED, which is half by AE, which is 12, by the height ED, which is 144 over 5, which equals 680.4. And so that is our area. So it's a bit long-winded, but none of these steps individually were particularly difficult. There's no particularly tricky things. There's just a lot of steps in this question. But yeah, that would have been a hard question to get. But I think the most important thing is to break down this rectangle into its parts, so that we can eventually find the area of this.